So thank you again, everybody, for joining us for this workshop to go through the Ouster SDK and what you can do with it. I am Tom Gray, coming to you from Ouster headquarters here in the sunny Mission in San Francisco. I'm just here to lead things off, but Christoph, who I'll introduce in a second, is really the star of the show here. So what we're going to do today, we have just a few housekeeping items to start. So as with all of our webinars, we're going to record this webinar and we'll be following up with an email with the recording. The email should be coming in tomorrow. So keep a lookout for that if you want to come back and watch portions of the webinar or the walkthrough. The second piece of housekeeping for this workshop, I'm using webinar and workshop interchangeably here, but really relative to what we've done, this is a workshop. I'll talk about that in a second. So we're going to have some time for technical Q&A here. So the purpose of this workshop today is to introduce you into how to download the SDK, how to get started visualizing the point cloud and doing some basic statistics on the point cloud. And then we are actually going to go into some, just kind of touching the surface on some of the machine learning tools you can use with the SDK. So Christoph is going to go through an example with Votenet, which is a tool, a library from Facebook. And so the focus of this workshop is going to be technical. And so please do send us in any Q&A you have during the call, but we're going to focus all the Q&A at the end on technical questions. And if there are any questions about the business or about our customers, please send them in, but we'll get back to you over email instead of answering those ones live here today. The last little bit, when Christoph goes through his walkthrough of all the steps of installing and doing some basic functions in the SDK, there are a few links that he'll reference or have up. So they are on the screen here. I'm going to pause for a second. If somebody, if you want to take a screenshot and try to follow along, we're also going to share them afterwards. So don't stress it. The three links, the first one is to download the SDK. The second one is for the SDK documentation. Both of those links are also on our website. The third link is the link to the GitHub repo for Votenet from Facebook Research. So you go there and you can download the repo and go from there. So with that, so I'm going to now hand it off to Christoph, who's put together a great walkthrough of how to get started and do some useful things with the SDK. Christoph is our field applications engineer here in the Americas. He works with our customers, helping get them deployed, and works quite a bit with the sensor. And so he's the perfect person to do this. So with that, I think that's everything we had to cover to get started. So I'm going to hand this off to Christoph now. And we will go from there. So I'll be back in about 35 minutes for Q&A.
Thank you for that intro. And hello, everyone. I'm Christoph Korda, Field Application Engineer here at Ouster. And today I'm going to be walking you through how to use the Ouster Python SDK. We're going to start out with a little bit of a quick start to get you guys up and running very, very easily. You'll see very quickly how easy it is to get this installed using your standard methods with Python, pip installing this. And then we'll roll into a quick example of getting some sensor data from a live sensor and taking that data and doing something fun and interesting with it. So in this case, we're going to be doing some statistics on it. We're going to grab the precision or the standard deviation of a pixel and then also determine the mean of that pixel. After that, we're going to do an even more fun example. We're going to take the data coming from the live sensor here in my room, as we all are these days, and we're going to apply a machine learning algorithm to it. Now we're just borrowing something from Facebook. It's called Votenet, and we're going to hook up the Python SDK directly to Votenet, and I'll show you guys later on where in the code we do the small modifications to the code straight from Facebook to make that happen. All right, for now, let's dive straight into the Quickstart. So here we have, on the left here, we have the Ouster SDK Quickstart guide. You can see here, we'll provide in the webinar the link as well, but you can see the link right here on how to access this documentation. You can also just do a quick Google search for the Ouster Python SDK, and it'll quickly lead you to this link. So this is your reference documentation for everything that you're going to see here. You have the quick start, you have some great examples and some basic concepts, and then you have the API reference, which is really useful to just get down into the nitty-gritty exactly how each one of these functions and objects and classes work so that you can actually apply them quickly and efficiently to your specific application. So, all right, let's just jump straight in. So what I've done here is I've just created a little folder for myself. Right now, all we have in there is the Ouster SDK stats.py, which you'll see how we're going to hook that up later. But for now, we're just going to start completely fresh. Like you never had this, you've never used it before. All you have is Python installed on your machine, and we're just going to follow the steps for doing that. So one of the best steps to do right away is to create a virtual environment. We have that in here in the documentation. You can see here it says, hey, it's a good idea to do this. You can do a virtual environment, you can activate it, and then you can do an upgrade to your pip once you've created that virtual environment. So let's do that. Let's actually go in and create a virtual environment. So we do that pretty simply just by picking the Python that we have installed already on our machine, whatever version you want, and then we're going to create an actual virtual environment from that using venv, and I typically just call them venv as well. So the second venv is actually the folder name that the virtual environment is going to live in. So if we execute that, in the background, it's actually copying everything from Python 3.8, putting it into the binaries inside this virtual environment. So if we look at this now, we should have, yep, there it is. We have a new folder called venv. And now what we have to do is we actually have to activate that environment so that we're actually working within the Python environment that we just created and not accidentally working in the Python environment that lives on our machine for the entire machine. So this will be a very localized virtual environment. So to activate that, we're going to say source, and then we're going to go into the folder venv, into the folder bin, which is for the binaries, and then we're going to run the activate script. And you'll see very shortly it's going to give us a little indicator right here that now we're in the virtual environment. And once we're in the virtual environment, now we can start setting it up and getting it ready for what we actually want to do with the Python SDK. So the next step is let's just install pip to make sure that everything is installed correctly from the beginning. And then if you ever want to add more packages other than the Python SDK, you can always do that. So the way we do that is we just call Python 3 -m pip, and we're going to install and upgrade our pip. Oh, and it looks like I misspelled it just slightly, so let's add the L there, and now we'll upgrade our pip and install it. And there it goes. Great, so pip is properly upgraded in this virtual environment. You may have already done this previously outside of your environment, but because we've started a new virtual environment, we want to make sure that everything's upgraded and installed because we're starting basically from a fresh vanilla Python. So next step is immediately we can go straight to installing the Python SDK. In this case, we're going to install the Python SDK, including the examples. And the way we do that is I'm just going to copy and paste it over. Now I'm using ZSH, so for any ZSH lovers out there, you probably already know this, but you need to add quotes around this because of the parsing of those square brackets. So let's do that. And this step is actually going to install everything that we need from the Python SDK directly into my environment. It's also going to install all of the dependencies and things that are needed for the Ouster SDK. So it's you can see all the packages that it's collecting and installing right now. And just like that, it's done. It's actually pretty quick. So what we're going to do next is jump straight into a very simple example where we're going to actually stream data from a live sensor. So you'll see here we have an actual quick call that you can use that's straight inside the Ouster SDK examples. And all we're going to need is the sensor host name. Now, so that we can directly use that command right there, we're actually going to export the sensor host name of my sensor in this case, but for whatever your sensor host name will be, this is what you would replace it in. So if you look here, I'm pasted it in here. So basically this is my sensor host name, and we're going to export this as an environment variable for us to run and use right now. And so when we copy over the Python example right here for playing data from a live sensor, it'll be able to use that environment variable directly and actually get us some sensor data. So let's give this a shot. And just like that, the quick example is done. You saw we went from pip installing the Python SDK with the examples, exporting the hostname variable, and now with one command, we've actually plotted some live data here. So this is me right here waving my hand in front of the sensor. And this is my beautiful room that is a little bit dark right now based on the signal kind of adjustments that are being made, so the scaling. Now you can change the scaling however you'd like. This is just the scaling that we've currently chosen in this room. But if you ever want to, you can change the scaling. You can make it more adaptive. And we actually have some auto exposure features that are coming out in this SDK very soon to help you really get the best and see as much as you can in here. So this isn't representative of the actual dynamic range of the sensor. The dynamic range of the sensor is very high, so you should be able to see everything in this room if you scale the bits properly. Okay, so now we've seen how to very quickly visualize the sensor data using this example. And the way this is happening is described right here. So essentially, we're calling the client.scans.stream. So stream means we're going to be streaming data from a live sensor. We're calling that with a closing function, so that way we don't have to, if we can't forget essentially to close out this stream, close out the lidar port, and do all these things. So it's a really nice way to do this without accidentally leaving one of your UDP ports open, and then you won't be able to contact the sensor later on. So this is good practice. So with closing is how we're doing that. And then the stream just basically needs a few things. It needs the host name, which we provided right up here. It needs the lidar port, which I've already set it to the default, which is 7502. And then complete equal to false just means instead of only providing complete scans, we're going to accept all scans, even if they're incomplete. So let's say like one of the packets didn't arrive, there was a network interruption or something like this. We're still going to present it because we basically just want to present the true and actual stream as it came from the sensor and it arrived to this computer. And then basically we go from there. All we're doing is we're going to do a while loop while our variable show is true. So basically indefinitely. And then we're going to loop through the scans in this stream. So the stream object basically creates some iterables, and we're just going to scan through those or loop through those using scan. So take that scan variable, bring it in here, and we need to call the client destagger. So the destagger basically makes sure that each firing of the array is properly aligned and isn't staggered. And you can see what that would look like if you didn't do the destagger. That's definitely something that I encourage you to do and check out. So that destagger is basically going to need the metadata from the sensor. And the metadata is basically things like the intrinsics of each beam, the lidar mode. So are we at 1024 by 10 hertz mode? Are we in a different mode? And then any other metadata that's included with the sensor is part of that. Now that's part of the stream when we call this in the background. It actually collects that metadata from the sensor itself. So it sends some queries to the sensor. It gets that information back, and then that's what we're using right here to do the destagger. And the destagger is also going to have the pixel offsets, and that's what really destaggers the image. So, and then we want to tell it which channel, or in this case, which field from the sensor we actually want. So we do that by calling the client.chan field, and then you can use any of the data channels that we have available. In this case, we're using signal, but you also have range, reflectivity, and ambient or near IR. So once we have that, we do some simple scaling to it. You can see the simple scaling right here. And again, you can make much better scaling if you want to see some of the darker areas in the room. You can absolutely see them. There's definitely illumination happening there. This scaling is just a very, very simplified one. And then all we're doing is we're using a standard Python available package called OpenCV. In this case, it's called CV2. And we're doing CV2 and saying, do an image show. So show the image of signal, which is the variable that we created here. And then just wait for the escape key before we close everything out. So it'll just constantly loop until we hit the escape key. And there you go. I've hit the escape key and it closed us out. Okay, now that we've gone through that live streaming data example, let's see how we can use that to do something more interesting, like taking the live streamed data and doing some statistics on it. So basically what we're going to do is we're going to leverage everything that we see here, and we're just going to wrap some extra code around it to do the statistics. And we're going to use nothing but what's available in Python from Python libraries, and you'll see that in a moment. So first, let's see what we have in our folder. And here you can see we have the Ouster SDK stats.py. So we're going to open that up really quickly and take a look inside and kind of step through the code so we can see how we leveraged this previous example. So first of all, let's just see this example right here and see where we have it. So basically that example is living right down here. So we're starting here with closing and the show true. I've added in here a little declaration of a list that is going to be my buffer for later on. And the rest of it is all part of it. Now, one thing I've added here is I want to actually get the range, not just the signal, because we're actually going to do some statistics on the range data itself. And then real quick, let's jump right back up here to the simple declaration. So first thing, we're declaring obviously the client import. We're going to import closing like we needed to previously, and then NumPy, OpenCV, and a statistics toolbox for doing the mean and the standard deviation. Then as before, we are declaring our host name. Previously, we did this on the command line using the export feature so that we had an environment variable. In this case, we're going to declare the variable directly in our script. And same thing with our lidar port. We're going to declare that variable and set it to the default UDP port of 7502. Then we're declaring num frames, which is basically going to be the number of frames that we're going to keep in the buffer to do the statistics. So all statistics will be done on the last 10 frames of data. And then these here are just declaring which pixel we are going to be using of interest. In this case, we're using a single pixel so that we can take 10 samples of the exact same pixel and see how much that pixel varies in terms of standard deviation, and then where the mean of that range reported is. So other simple declarations that are needed later on. Some of these are for drawing the text on the images, and then some of them are just initializing variables for the average and the standard deviation. So as in the example to the left, we're just taking the exact same code. We're going to do with closing. We're using the host name, the lidar port. We're going to do incomplete frames if we need to. Anything that comes from the sensor, we're going to work on it. Then I'm initializing essentially a range buffer that's going to be the area of interest. AOI is for area of interest. So we're going to buffer the last 10 frames as we mentioned earlier. So same as before, we're going to take each scan inside the stream, and we're going to do some more interesting things with it. First of all, we're actually going to grab the range information here instead of just the signal. We're also going to grab the signal because it's interesting to stack them together, and you can see how easy it is to stack the data using the CV2 methods. So the only difference here, as you can see, is instead of the signal Chan field, we're using the range Chan field. Here I've created a scaling very similar to, if not identical to the signal. And that's just so that it presents a little bit cleaner, and we can actually hopefully see, in this case, the entire room, and you'll be able to see what's in the room now. Next, we basically slice into the range data using the area of interest that we declared above. And then we append that data to the range buffer, the range AOI buffer here. And so that way we're going to stack up essentially 10 frames. And the way we do that and make sure that we always keep 10 frames inside of this buffer is using this little if statement here. So if the buffer gets above the number of frames, which is 10, then we're going to pop the first element, and since we just previously appended the newest element, we should be back to 10, and now we'll print what that range buffer looks like. Okay, and then once we've done that, we're actually going to run the statistics on the entire buffer of 10 frames in this case, and we're going to convert them into an integer just for cleanliness and simplicity. So we'll do average, we'll do standard deviation. And then we're going to first do a gray image. Now this is the gray image. Basically, this is the 0 to 255 gray image, which you can see back up here. We scaled all of this to 255 using unsigned int 8 bits. So we're going to create that gray image first, and then we're going to convert it to color. And the only reason we're doing that is just so we can add some colored text later on. But if you ever wanted to, you can make this a part of yours as well, or you can leave it out. It's not that critical. All right, so next thing I'm going to do is I'm actually going to draw a rectangle so we can actually visualize what part of the scene or what part of the image that we are looking at, the area of interest, and where we're doing the statistics. Like what pixel are we doing the statistics on? And then I'm also going to put text into the image, and that text is just basically going to be the range precision, the range mean, and the last number of frames that these statistics were completed on. And then we have to show that image using CV2 imShow. And then, same as before, we are going to have the wait key waiting for the escape. The escape is this section right here. Basically, it's a hex value at max value of FF. Cool. So let's exit out of this and actually run it. So in order to run this, we are just going to do as we did before. We're going to do Python, and then we're going to run Ouster SDK stats.py. And here we go. And here we go. We can see it's printing out, like we saw in the code, it's printing out the last 10 ranges that it's collected in the buffer and the frame ID here. Now, as you saw, this popped up. We'll bring this over here in focus. Apologies for it being a little small, but that's the best we could do right now on this screen. But as you can see here, we have the pixel right here is this little green dot, and then the text that we've applied to the image, which is basically, hey, this is the last 10 frames. We're doing the range precision, which is hovering around 3 to 4 millimeters on the cabinet behind me. And then the range mean, and this is again in millimeters, so we're about 3 meters away from me right here. And you can see this is me here, live sensor, and we can actually see the data change. If I put my hand here in front of it, now we can see that the range goes down to around 3 centimeters, 3.5 centimeters, about 350 millimeters. And then the precision, same thing, around between 2 and 4 millimeters of precision there. So it's your standard deviation. So this is a perfect example of how easy it is to quickly write a script, get some data, and do something useful with it. So I'll leave this running in the background for a bit. And we're now going to move on to the really fun section, which is taking everything we've learned so far and applying a machine learning algorithm to it. Okay, so now let's actually stop this and let's switch over to another window. We're going to start fresh and let's check this out. So what I have in here is I've actually already cloned the Votenet from Facebook. This is the machine learning algorithm that we talked about earlier. And here's where you can get it, essentially. This is the link here, and we'll have this in the webinar as well. And basically this is from Facebook Research. It's called Votenet, and it's a pre-trained machine learning algorithm for doing basic object detection. So in this case, you can see it's picking out things like couches and tables and things like that. And we're going to do something similar with the objects that are in my room right now. You may have already spotted what we're going to be looking for if you had a keen eye. So hopefully you have, but we'll find out soon enough. So essentially, it's got good documentation here, and all we did is we took all of the code here, we cloned it locally, so that's what's in our Votenet folder here. And actually, let's change directories into that before I forget. And now we're in there, and we can see we have all of the same files that we've cloned from here, and we also have some extra files in here that we've added for ourselves for practicing and also the pre-trained algorithms. So here's the pre-trained model. You can actually get it at this link right here, and that's where we got these pre-trained models here. So, and we dump those into the same folder here. And just as before, we are going to use the Python SDK for Ouster and make some small modifications to the code. So the code that's actually being modified in this case is the demo.py. So we took the demo.py, copied it, and we made Ouster demo.py. And we're going to jump in there real quick just to see some real simple modifications that we made using the Python SDK. So going in there. So we've made it kind of easy to find the changes from that Ouster has made. And here they are. So essentially we just need a couple helper functions. So one is the get geometry of the bounding box. So at the end of the Votenet, it's going to identify an object and it's going to give you a bounding box of that object. So we need that so that we can then label the actual points, the 3D lidar points that are within that bounding box, and color them and make it kind of interesting and fun for the humans to look at. And then we also need to have a little function here to do pull the data from the sensor itself, so make the sensor data as the source. And you can see it's very similar to what we did before. So we're getting the metadata. In this case, it's running, this one is running for a PCAP, but you can also do it on a sensor directly, which is using a host name. So you can see right here, this is where we actually build the plugin to actually connect the Ouster sensor directly to this machine learning algorithm, Votenet. And then further down, there's a little bit more. There's a couple more things that we had to change. So here, we're actually bringing in the source data. So earlier we set it up to actually call the data. Those were the calls for make source. And we're going to take the metadata. We're going to do the XYZ lookup table based on the metadata. Now that XYZ lookup table is basically, it's using the metadata which has the beam intrinsic. So where is each beam pointing in altitude and in azimuth? And it's building a lookup table so that we can actually create the XYZ of the points. So the raw data coming from the sensor is actually just range, signal, reflectivity, and the near IR. And then you have to query this metadata to tell you how to take that range and do something useful in terms of making it an XYZ point cloud. So that's what's happening here. And then we get the pixels per column. So that tells us, you know, maybe you have a 64 channel sensor from Ouster, or maybe you have a 128 channel. So that pixels per column will tell you how many channels you have. So in this case, we're running a 128 channel sensor. So our pixels per column will end up being 128. And then the columns per frame, this is basically, we're doing in a full rotation, how many measurements are we taking in the horizontal? And that's the columns per frame. So in our case, we're going to be running this sensor in the 1024, so it'll be 1024 horizontal measurements per frame. And we're doing it in the 10 hertz mode. And then there's a little extra piece of viz code so that when we get all this data from the sensor and Votenet has done its job, it's identified the objects, we can actually make it look good. And that's pretty much all the changes that we made from the kind of vanilla straight from Facebook Votenet. So let's exit out of this. And let's actually remember to export the sensor hostname. So in this case, we got to bring this back in. So copy and paste this in. So we're in a new terminal, so we have to do this again. New terminals, you have to export the variable names once again. So now that we've done that, we should be ready. And we'll see if we can find this in the history here, rather than typing it all out. So here's the command to run this Ouster Pi demo on the live sensor using the number of points as 60,000, and we're going to use the Sun RGBD method of machine learning for this. So the model, I should say. And let's add in here the sensor host name. So this is going to tell us what sensor I'm connecting to, the number of points we want for each inference, the model we want to use. And then sensor is just saying, hey, we want to use a live sensor. If you wanted to, you could do the inference on a PCAP, and all you would do is change this to PCAP instead of sensor. So let's give this a shot. And it wants us to correct this, and yeah, sure, we can correct it to Python 3. Oh no, we have a module. So this is actually an excellent teachable moment right here. So what we need to do, and some of you might already have realized this, is we did not activate our virtual environment. So I actually don't have a lot of the things that I need, the packages installed from Python that I actually need for this. So let's go back and actually do that. So let's source. In this case, we've created our own virtual environment for the Votenet and pre-installed the packages for that, so you don't have to wait through all that. So once we do that, now we can go back here and rerun this command now that we're inside the actual environment that we're supposed to be in. So let's give this a shot one more time. The only thing that might go wrong here is that maybe we haven't, now that we've activated a new environment, we haven't done the host name. Let's see if that fails. If it does, we know the answer. We just have to export hostname. And it's taking a minute here. It's constructing the model. It looks like it didn't get much point cloud data. It says 0, but it did. Okay. So what we see here, this is the room that we're in right here. And we can see that it's identified 2 objects. So we can see that here are also in the text. Finish detection, 2 objects detected. So we can see here, it looks like it's picked out the chair, which for anybody who guessed earlier, that was definitely one of the objects we were looking to see here. So we've picked out the chair, and it looks like it's also partially picked out the couch here. So you can see there's a couch kind of picked up behind it. Maybe it's a chair there. Maybe it thinks it's longer than it's supposed to be. Now what's cool is we can actually rerun this again just by closing the window. And it'll actually start all over. And now it looks like it only detected 1 object, so my guess is it's probably just the chair. And sure enough, there it is. So now we can see that it's picked out a bounding box for the chair, and then we've, using the viz helper that we saw earlier, we've colored this and kind of identified the points that are identified as the chair. So that's really how easy it is to take the Python SDK and connect it to something that's actually real and useful, already available, open source from Facebook using Votenet. Super cool example. And just for fun, what we can do is we can actually move the chair and see how it's going to change. So stand by right now, and I'm going to go and move this chair. All right, we've moved the chair. Now let's see, let's run this again. We'll close this out. It'll automatically run again. And it looks like it's back to 2 objects detected. Let's see what it picks out. And sure enough, it's still found the chair. I've moved it, but it still found it. And it looks like it's done similar to before. It's kind of identified the couch, maybe a little bit crooked. And again, these are all things that you can tune when you start playing with these machine learning algorithms. Each one's going to be a little different. Each one's going to have some tuning parameters and some hyperparameters that you can tweak to make this work a little bit better. But again, you get to see how quickly and easily you can connect the Python Ouster SDK to work on the data and use open source available tools. And that's it. That's it for the examples and the kind of walkthrough on the Ouster Python SDK. So thank you so much, everyone. We are now going to switch over and open it up for some questions from y'all. All right, thanks again.
Awesome. Thank you for putting all of that together, Christoph.
Yeah, absolutely.
That was great. Let's see here. Sorry, my computer's jumping back and forth. But great. So we're gonna open it up to Q&A. So please plug in your questions in the chat if you have them. Before we get started, there was just kind of one extra little bit that I forgot to mention at the beginning, or kind of wanted to put some extra emphasis on. And that's we didn't really explain, I mean, kind of on the high level, what the SDK is, why we built it, and where it's going. So just kind of quickly in, a minute, the SDK really is a layer to interact with lidar data with Python, like put as simple as possible. And Python's not, it is the most common, R&D language used for algorithm development and work like that. And Python hasn't historically been easy to use with lidar sensors. So we built basically a layer to make it easy to use Python to interact with Ouster lidar sensors and quickly iterate and develop algorithms. So that's the main goal. So as we keep working on this SDK, this is really just the first initial release, but there will be many, many more. And our goal as a company, we recognize that our customers are kind of the success in building the lidar ecosystem is just building more applications and making it easier to develop with lidar data. So the purpose of this SDK, we're going to continue to make our developers' lives easier, the algorithm development faster, and build a much bigger ecosystem around lidar sensors so that it becomes that flywheel effect of lots of tools, similar to many online ecosystems out there built on Python, but many more tools that are off the shelf that you can pick up and use when you're developing things to make your life easier and faster. So that's our goal here, and this is really just day one of getting that going. So we're really excited about this. There's going to be a lot more on this, and please, if you have anything that you've developed that you want to share or talk about, we'd love to be able to share that with others, so that other people can get good use out of it. So okay, I'll stop there. There's kind of my spiel on the Python SDK. As far as where we're going next functionally, we are going to be adding C++ native support, or native SDK, as well as adding a lot more command line utilities to the SDK. So that's sort of in the immediate future and what you can look out for from development for the tool. And with that, let's move into answering some of the questions that came in during the webinar. So I think I'm just going to be the Vanna White here and feed these over to Christoph, who is much more qualified to answer them than I am.
Thank you for that.
I'm just speaking the truth. First question. So the SDK can handle, it's in Python, but handles live data. How does it keep speed while handling the live data?
Yeah, absolutely. So basically, the Python SDK is built primarily on C++, so it's basically a wrapper to all of the background C++ that's actually running this. So it's actually running very efficiently because of that. So that's how we keep the speed up. So it's actually, you can actually see the code that's being used in the background for this. It's all up on our GitHub page for the Ouster example. Any efficiencies that have been built into that C++ code on GitHub are also in this, because it's actually just referencing all that same code.
Cool. Next question. So does the SDK work on Windows?
Yeah, absolutely. So the beauty of this SDK, and actually why it was such a big milestone for us to get to the developers out there in the world like yourselves, is that Python is operating system agnostic. So anywhere that you can install Python, you can install this SDK, like you saw just by doing that pip install. So it's available on the pypy.org packages. And so as long as you can have properly installed your Python on Windows, then yeah, you just go through the normal process of doing the pip installation.
Cool. Perfect. We're going to cruise right through these. So the next question is using the Python SDK, is it the same process on Anaconda as what you walked through today?
Yeah. So it's pretty much identical. The only difference is instead of creating the virtual environment using the venv virtual environment packages, you would just build your virtual environment however you normally do with Anaconda, and then once you've activated your Anaconda environment, then you do the same thing. You just do a pip install for the actual packages from Ouster, and that's actually, again, why it's so amazing to have this available, is that it's very agnostic to your operating system, your virtual environment, all these things. As long as you have the pip installed there, you can easily do it that way. But you can also go and grab the package source if you wanted to as well from the link that we had talked about earlier, directly from pypy.org, and then build it from source.
Cool. So next up, so the PCAP file captured from a live lidar stream has many points that are zero values, like i.e. like an XYZ, like a range value of 0. What does that mean?
Yeah, so it can mean a couple of different things. So depending on your sensor generation, if you have a generation 1 sensor and it's like less than 64 channels, then you'll get 0 data for the channels on older firmware. You'll get 0 data for the channels that are not activated. So that's one case. So like if you have a 16 channel sensor, you'll get the other 3/4 of the data will be essentially zeroed out. The other reason you would see a 0 range is if that laser or that channel didn't get a return. So let's say the object is really, really far away and the light never made it back, then that would be reported as a 0.
Cool. Great. So next, let's see. So the Ouster, so this is getting a little more technical in the file conversions. The Ouster SDK converts the PCAP file into a frame-by-frame CSV. Is there a way to get a frame-by-frame .pcd file or .bin file from it?
Yeah, there's certainly a way to do it. I don't currently have an example for that. I can go maybe take this back to the software team who developed all this and see if we can make that as an example, because I know that's going to be very useful for a lot of people, especially if they're working in ROS. So yeah, I'll take that back to the team and see if we can make that happen. But essentially, you could leverage a lot of the data management tools inside of Python to potentially do something like this. So once you get the CSV data, it has the XYZs at, I think it's the last few columns of the CSV. Then you can bring those into some kind of a data frame and then do a data frame export to PCD if there's some tools available for that. And I haven't researched that yet, so I apologize. I don't have a perfect answer for that, but I think we can get that figured out.
Cool. Cool. So the next one, this is also kind of a little specific about a method, but it's is there an example of how to use the sample method of the scans object? I'd like to collect a bunch of scans and average the range over time with NumPy, but wasn't able to make it work.
Yeah, actually, that's exactly I think what we did here. Oh no, we're talking about the scans instead of the stream. Let me check really quickly. I can't remember if we have an example of that.
Cool, but I mean, I take it that is possible, and maybe just reach out to us and we can help out with that.
Yeah, definitely. Yeah, I haven't played as much with the scans method as I did the streams, but it should work essentially the same. So I don't know if you remember, but the stream is actually basically just an object with a bunch of iterables of scans. So the scan method should work very similar.
Yeah. Cool. Yeah, we'll follow up directly with who asked that question and make sure you got your question answered too.
Cool.
Great. And so let's see next. So let's see. 3 questions. I'm going to order them. So first, what would cause incomplete scans, and how do you detect incomplete scans?
Yeah. So the primary thing that would give you an incomplete scan would be some kind of a network interruption, or if your computer's having trouble keeping up with the packets coming in. So like the CPU is getting overloaded and it maybe has to drop a packet based on the threading and things like that. Like especially if there's other things going on the machine, like you're bringing in camera data as well, it needs to be able to pick which one it's gonna work with. And if it runs out of resources, it'll just kind of selectively drop whatever it needs to. So that's one way where you could have a partial scan where your scan would be missing, let's say if it's a single packet, would be missing 16 columns of data. And then what was the follow-up question to that?
Yeah, well, there are a couple. They're kind of related but different. So the next one is if we have any data analyzing the difference in latency between Python and C++ for running the sensor commands.
I haven't not seen any direct data yet, but I can say having used it just kind of anecdotally. I was previously using only the C++ code that we have on GitHub, and then switched over to the Python SDK, leveraging the same code. I haven't noticed any difference in speed, but that's, again, that's only qualitative. I don't have any quantitative data on it yet. I'm sure we can get some of that information from the software team though.
Cool.
Back to the other, I think there was a follow-up question to the previous one about the drop packets. I think it was, how do we detect it?
Oh, yes.
Yeah. So on that, you can essentially use there's measurement IDs for each measurement that comes in. There's also frame IDs. So you can use those in the Python SDK to kind of just check and make sure you haven't skipped over a measurement ID or a frame ID. If you're checking, measurement ID would check that you've missed data within a frame, and then a frame ID would see if you've missed an entire frame.
Cool.
So if you read in the ID number and it skipped from like 1 to 4, then you would have missed 2 frames there.
Cool. And last question, I think this is probably a good one to wrap up on here, is if we have any demo PCAP files to get started on.
Yeah, definitely. Yeah, we have a bunch of example data hosted on our website, available at ouster.com/downloads, or under the resources page. You also have a link that'll get you there.
Perfect. And actually, there's if you just go into the Ouster SDK documentation in the Quickstart section, there's also a direct link in there to go grab some sample data. So yeah, it should be in a bunch of places.
Nice.
Cool. Well, this was great. Thank you so much, Christoph, for getting organized and putting together this whole workshop. And thank you everyone who attended for all these questions. We would be happy to answer any and all other questions that you have. Please do reach out. We're eager to get everybody using this tool. So feel free to email us. The email on the screen here, lidar@ouster.io, will work, and we'll route that to the right place. Or please feel free to just ask questions on our GitHub. Happy to field questions or bug fixes or feature requests through GitHub. Great.
Yeah.
So with all of that, we'll wrap up, and everybody can carry on with their Thursdays here. Thank you everyone for joining, and we really hope you enjoy getting a lot of value out of the Ouster SDK.
Yeah, thanks a lot, everybody.